Hey y'all, it's Miss Power. I'm in my kitchen next to a window, so the sunlight might be absurd, but that's fine. I'm gonna work through this test review for you. It's the best way to study is honestly to do the review later tonight, while I am doing it on YouTube. All right, let's get started. For the first bit, let me make this smaller. There we go. For the first bit, for each table, we're going to determine whether the pattern is, and this is the pattern, linear, exponential, quadratic, or something else, right? And then I'm going to write equations for each of these. To be honest, on the test, you're only going to have to pick two of these to write equations for. So if you're confused about, say, quadratic ones, you can just kind of let it slide. All right. For the pattern for this first one, the first thing we're going to check is we know that linear is adding or subtracting the same thing every time. We know that exponential is multiplying or dividing the same thing every time. We know that quadratic is this second difference is the same every time. And if none of these are true, we say none of these are true. So let's check these ones. Let's check if we're adding or subtracting the same thing every time. From negative 25 to negative 11, we added 14. From negative 11 to positive 3, we also added 14. Promising. From 3 to 17, we added 14. And it goes on and on. Right? So it looks like this one is linear because we're adding the same thing every time. There are certain patterns for writing the recursive equation and the explicit equation for linear functions. The recursive pattern is you tell me what f of 0 was, you put a semicolon, then you write that f of n is equal to f of n minus 1 plus 14 every time. So the two parts of this are, number one, you told me the y-intercept, where x is 0, and number two, you told me how to get from one to the next one, right? The pattern is that it will always say this, and then this is what you're adding or subtracting each time. For explicit, there's also a pattern. The pattern is y equals mx plus b, where this is your common difference, and this is your f0 term. Right, so here we have that f of x is equal to 14x plus 3. Well, we should see that both equations have a 3 and have a 14. We're kind of expecting them to be similar because it's the same equation, just in a different format. All right, let's look at this next one. Let's check if it's linear. Here we are adding, nope, we're subtracting 1. Then we're adding 1. Then we're adding 15. Then we're adding a whole lot more than 15. Let's use the calculator. We've got 81 minus 16 equals 65. And then 256 minus 256 minus 81 is, then we add 175. This is not linear. Straight up not linear. Let's check exponential. 1 times 0 is 0. 0 times 0 is not 1. So we know it's not exponential because they're not multiplying by the same thing. All right, let's check the second difference. From negative 1 to positive 1 is plus 2. From positive 1 to positive 15 is plus 14. Already now we know that it's not quadratic because the second difference isn't the same. So we will write none of these. And we'll be done. If you really care to know, this is the quartic function. Nice. All right, scroll down, scroll. Next one, let's check for linear. Negative 3 to 0 is plus 3. 3 to negative 3 is minus 3. Already we know it's not linear. It looks like we're not multiplying by the same thing either, because if we went from negative 3 to negative 12, that would be times 4, and negative 12 times 4 is not 27. So we know it's not exponential. Let's check for quadratic. I'm finding the difference. So that's my first difference. Over here, did I do my second difference in green? I'm pretty sure I did. Yeah, nice. My second difference from 3 to -3 is -6. And then this one is 6 smaller, and this one is 6 smaller, and this one is 6 smaller. Looks like it is quadratic. There also are patterns to these for the recursive ones. So the recursive, we start with, oh no, let me do it in orange. We again start by saying what f of 0 is. Then f of n equals f of n minus 1. That's always the same. What we're adding to this is we're basically trying to come up with a linear function, a y equals mx plus b equation for these orange first difference numbers. Here's how I'll do it. I'll immediately use this as my m in my y equals mx plus b situation, and I will use the difference that ends at 0 as my b. Right? The thing I'm adding to end up at 0 is what goes in the back here. So that's the systematic way to make recursive quadratic equations. For explicit, we kind of get creative, right? If I drag this over, there we go. And I added in an x squared column right here. I know that my quadratic is going to involve x squared. So that's what the equation for quadratics involve. So I can find x squared for all of these. And now I can kind of pattern match. Now this is the creative part. I look at my red column of x squared here. And I say, what do I do to this column in order to end up at the column that I actually want? It looks like I'm multiplying by -3, right? 1 times -3 is -3. 0 times -3 is 0. 9 times -3 is -27. So once I find a rule that works, I'll make that my explicit equation. So f of x equals -3x squared. Right now, this is what we got. This is like the pattern matching creative side, where I would make an x squared table column and then see what do I do every single time to turn x squared into what I actually want. Right, for this one, here we add 5/6, and here we add 5. So plus 5/6 plus 5. We know it's not linear, so we'll erase that and we'll check exponential. Here we multiplied by 6, here we multiplied by 6. This looks good. And then it turns out we multiplied all of it by 6. So this means our pattern is exponential, not explicit, exponential. Recursives for exponential also start with f of 0. They also start with f of n equals f of n minus 1. This part is always the same. And then this part on the back is the rule. What are we doing each time? We are multiplying by 6. Nice. Just like linear, that's explicit, has the form y equals mx plus b. The exponential has a pattern that is a times b to the power of x, where a is your f of 0 and b is your common ratio. So here my explicit function is 1 times 6 to the power of x. We could simplify that to just be 6 to the power of x if we really wanted to. All right, first one. Scroll. Find the slope of the line that passes through each pair of points. We will use the slope equation, y2 minus y1, x2 minus x1. So here the slope that passes through these 2 points is -42 minus 24 and 9 minus a -2. -42 minus 24 is -66. 9 minus a -2 is the same thing as 9 plus 2, which is 11. which simplifies to negative 6. I did the second y minus the first y, and the second x minus the first x. To make that line dotted. Okay. Same thing for b. The slope is second y minus first y, second x minus first x. We can read this as negative 9 plus 3, which is negative 6. And we can read this as negative 4 minus 20, which is negative 24. The negatives cancel. And 6 divided by 24 is the same as 1 over 4. Nice. Multiply. All right, now it's time for distribution. To distribute. Let's change colors. Okay. When we've got one term on the outside of parentheses with a couple terms in it, we just want to multiply this term times every single other term. So first we've got negative 2x times 3x, and then we add negative 2x times negative 4. Alternatively, you can write this as minus, because there's a minus in the middle, negative 2x times regular 4, positive 4. All right, so like this. For these terms, I do negative 2 times 3 is negative 6, and x times x is x squared. For these terms, I see minus a negative instantly becomes a positive. 2 times 4 is 8. There's only one x, so there remains only one x. I then know that this is my final answer. I know this because the red first term is x squared, and the green second term is just x. Because they aren't the same variable pattern, we can't combine them with addition. So this is what you do if there's one term on the outside and there's two terms on the inside of parentheses. If there are two terms on the outside and two terms on the inside, we basically just do the same thing twice, right? So we just do 3x times 2x and 3x times 4, and then also 1 times 2x and 1 times 4. So 3x times 2x plus 3x times 4 plus 1 times 2x plus 1 times 4. You can skip some steps if you want to. I'm just writing every single step right now. If you're thinking like, I could do that in my head, do it. Go for it. 3 times 2 is 6. X times x is x squared. 3x times 4 is 12x. This simplifies to 2x, and this simplifies to 4. I can combine these because they have the same variable pattern. They both have just x's. But I can't combine any of these, so I'm finished. Nice. Same thing, but with negatives, so let's do it. X times x is x squared. X times negative 3 is negative 3x. 10 times x is plus 10x. And 10 times negative 3 is negative 30. I again can combine these middle two because they are like terms. That means they have the same variable pattern. And I'm finished because there are no more like terms. All right, 4D. This is kind of confusing to people. You say like, oh, how do you deal with this 2 out front? Here's how you do with this 2 out front. Let's move this better. I'm going to distribute the 2 just into the first one. And then do this exactly like numbers B and C. So now I do 2x times 2x, 2x times 3, negative 10 times 2x, and negative 10 times 3. I combine my like terms. I'm finished. There we go. So again, for this one, you're just doing the 2 times the first binomial and then multiplying it to the rest. All right, now we do some substitution. This is substitution where I give you a function, I tell you what I want you to plug in, and you plug it in. So if the function is 3x squared minus 4x plus 1, and I want to plug in 2, I will just rewrite it such that everywhere I see an x, I put a 2. Same thing over here. If I want to plug in negative 3, I rewrite it where every time I see an x, I put in a negative 3. And now I'll simplify. When we do PEMDAS, it's exponents first, then it's multiplication, then it's addition and subtraction. So I changed the 2 squared into 4, and then copied the rest of it down. I changed the 3 times 4 into 12, and the 4 times 2 into 8, and then copied the rest of it down. And then I just did this in my calculator. 12 minus 8 is 4, plus 1 is 5. Same thing here. Exponents first. Negative 3 times negative 3 is 9. Multiplication next. A negative times a negative is a positive. And then I actually add all this stuff up and get 40. Moving on. Same deal. Every time I see an x, I'm going to plug in a 3. I'm going to do exponents first. I'm going to do multiplication next, and addition last of all. The thing I went really fast on is 2 to the third is just 2 times 2 times 2, which if we do the multiplication is 8. One more time. Every time I see an x, now I want to plug in a negative 2. If you plug this into a calculator, 2 caret negative 2, you will get 0.25. The reason that is because every time we see a negative exponent, we could have written it in the denominator of a fraction. Then when we do 2 squared, we get 1/4, which is 0.25. 3 times negative 2 is negative 6. And then this is negative 5.75. Or if you'd rather, negative 23 over 6. Nope, over 4. Nice. Keep going. All right, now let's do some patterns. Let me get a tea. Oh, I've been talking all day. All right, let's go. Use the pattern below to answer the questions. I'm going to color code this real quick. I think when I look at this pattern, the first thing I notice is that these upper 2 blocks, here, 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 and here, pretty much don't change. So when I draw my 5th figure, and when I draw my 20th figure, they're definitely going to have these 2 blocks up top. Then I notice that I've got a rectangle here, which is 1 by 2, so height 1, base 2. I've got a rectangle here in the middle, which is 2 by 3. I've got a rectangle here, which is 3 by 4. And a rectangle here, which is 4 by 5. So when I draw this one, I know it should be 5 by 6. You can do the little grid, make all the little squares if you really want to. I'm cool with it looking like this. Now the last part I notice is that there is a skinny rectangle, like a long rectangle at the bottom, which is changing each time, but it's the exact number of the step that we're on. So for this one, there'll be 5 of them. And for this one, sorry, I didn't do the green rectangle. Should be 20 high and 21 across. For this rectangle, or for this figure, it should be 20 long. All right, how many tiles will be in the fifth figure? 5 times 6 is 30. This is 2, and this is 5. So it's 30 plus 2 plus 5, which is 37 blocks. Okay, scrolling down, I copied and pasted the pattern so we can still see it. Write the explicit equation and write the recursive equation. Explicit means we're just looking at each one on its own and trying to figure out how we could have gotten there, right? So if we have this one, where I know n is equal to 3, I notice that this is 2, and it always is 2. This is 3, but it changes from figure to figure. So this one I'm going to say, every time I see a chunk of 3, I really mean n. And I'll do it for this one too, so you can see exactly what I mean. Right? This one's 2 and remains 2, whereas this one's 4 when n equals 4, so we kind of say that this is plus n. And then this middle bit is n times n plus 1. It's whatever step we're on times 1 more than whatever step we're on. Because that's the case for both of these, and to be honest, all of them, wow, so close. And because that's the case for all of them, we can write our explicit equation patterned off of this. We say both of them have a 2, so I write a 2. Both of the middle rectangles are n times n plus 1. And both the bottom long rectangles are just n. So this could be our explicit equation. This is not systematic. This is a little creative, right? So you'll have to flex these muscles of being able to recognize patterns and formalize patterns, which is still a math skill. It's just not what we think of when we think of math yet. But don't worry, I'll convince you. Okay, for recursive, what I want to do, copy paste, is I want to think of what came beforehand and how can I transfer this one? How can I change this into the next one? So I'm going to, in red, color over the f of 3 pattern. So if I copied and pasted the third step on top of my fourth step, I would get this. So when n, let me get a different color. When n is 4, I've added this one over here. I've added 4 to the side here, and I've added 4 to the side here. We could have counted this in 8. We could have counted this as like 4 and 1 and 3, or a lot of different things, right? I'm looking to find groups of 4, because my n is 4. So every time I see a group of 4, I can say, oh, that's probably plus n and plus n. And then this is just plus 1 straggler. Let's see it for f of 3. Boop, boop, boop. Right, if I color in f of 2, what did I add? I added this 1 straggler off to the side, so just 1. And then I added 2 groups of 3, which we can think of as 2 groups of n, because here our n is 3. So what does this even give us? Why are we doing any of this in the first place? This tells us that our recursive equation will be f of n equals f of n minus 1, as it always is. Plus, we add n twice, and then an extra 1 straggler. Then we write down what any of our initial conditions were. So we go up, we say, in figure 1 we had 5 blocks. So here, figure 1 has 5 blocks. This together is my recursive equation. Ooh, this video is going to be long. All right, let's go. All right, another creative one. At the beginning means time is 0. At 1 minute means time is 1. At 2 minutes means time is 2. They first want me to organize the information in a sequence in a table and give the next two terms. So I'll do that off to the side. Then I'll graph it off to the side as well. So for a table, I said when time is 0, 1, and 2, and the next two terms. My number of dots, so my f of t, is 1, because there's 1 dot here. Oops. 5, because there's 5 dots here. And 9, because there's 9 dots here. It looks like what's happening is we're adding on like another layer around the middle one. So we added on these ones. And then over here, we added on these ones. So we can kind of lead ourselves to believe that each time we're adding 4, which means this should be 13, and this should be 17. All right, graph the terms in the sequence. I'm going to... We want to say, what? 1, 2, 3, 4. It goes up to 17, so let's make this one, make this 15, 10, and 5. 0, 1 goes here. 1, 5 is here. 2, 9 is slightly below 10. 3, 13 is a bit more than halfway. 4, 17 is a couple more above 15. And we would leave it like this. We don't really connect it because we don't have decimal times in our pattern. We'll leave it like this. And again, that's just taking these two numbers and plotting them on our XY coordinate planes. Like 3, 13 turns into 3, 13, turns into this star. Let's scroll it down. I'll move my guy. Me. Is the sequence arithmetic, adding the same thing, or geometric, multiplying the same thing? We are adding, so this is arithmetic. We also think of this as linear. Okay, recursive and explicit formulas. If we think it's linear, then the explicit formula will be y equals mx plus b, and the recursive formula will be whatever f of 0 is, and also this pattern, which we always start with, and then how much we add or subtract here. So for ours, I actually probably should copy this table. That's the more useful thing. For our recursive formula, f of 0 is 1, and we are adding 4 every time. For our explicit formula, we're adding 4 every time, and our initial condition is 1. Again, this is what you're adding every time, and b is f of 0. And let me be consistent. I should have written f of x here. How many dots will there be in the 100th minute? This is when I use my explicit equation, and I just plug it in. 401 blocks. No, dots. Sorry. All right, last one, I'm pretty sure, and then the chart. Last sequence of dots we've got at the beginning, so that's t equals 0, t equals 1, and t equals 2. the chart, I'm going to do the chart right here. We have 0, 1, and 2. They want 3 and 4 as well. This was 3, this was 6, and this was 12. The pattern looks like it's doubling every time, right? 3 to 6 is times 2. 6 to 12 is times 2. So this would be 24, and this would be 40. Graph this in terms of the sequence. We go up to 4, 1, 2, 3, 4. We go up to 48, so I'm going to make this 50. 40, 30, 20, 10. To put my dots in, 0, 3 is down here. 1, 6 is a little bit more than halfway between the 10. 2, 12 is a little bit higher than 10. 3, 24 is almost halfway between 20 and 30. And then 4, 48 is almost near 50. Again, we don't connect the dots. If we did, it would look like this, but we don't. Is the sequence arithmetic or geometric? It is geometric. We can also think of this as exponential. The recursive equation thus is f of 0 equals something and f of n equals f of n minus 1. And then this is times or divided by something. Here it was times 2, so here we'll put times 2. F of 0 was 3, because that was the beginning, so we'll put a 3 here, and we're done our recursive formula. Explicit, we have a pattern. This is our pattern where A is f of 0, that's a 0, and B is the ratio. So due to our pattern, we get that f of x equals 3 times 2 to the power of x. If we want to know how many dots there will be in the 10th minute, we just plug in 10 to our explicit equation. Doing the exponents first, and then the multiplication. I'm pretty sure that's right. 24 times 3 is 72. That's true. Good. Again, these two, I used a pattern for, right? I used a pattern because I know it's exponential. And the very last thing, the chart, right? I'm definitely putting this on the test. We should be able to fill this in totally all by ourselves. So, let's start with equations. The linear equation has x terms. The quadratic equation has x squared terms. An exponential has numbers with x as the exponent. So x's are the highest order term. X squared, and you might have to multiply these out. So like an example of a quadratic form would be this. This is quadratic even though there are only x's, quote unquote, because if we simplified it, x times x would give us x squared. So it's the simplified form, we're looking for x squared. Also the highest order terms. We're just gonna, oops, boop up this over there. Nice. And then here again, x in the exponent. For our tables, linear means you're adding or subtracting by the same thing. And that's the first difference. For exponential, you are multiplying or dividing by the same thing. We call that the constant ratio. Then for quadratic, The second difference is constant. So this is how to check whether it's linear, quadratic, or exponential using a table. For graphs, linears are straight lines. Straight lines. Quadratics are what we call parabolas. Then exponential are these exponential curves. Ooh. Nope. Wow, I wish I could write cursive. All right. Last things last. Rate of change. Linear has a constant rate of change. Quadratic has a linear rate of change. And exponential has an exponential rate of change. Yo, that's the review. If you still have questions, you can email me. I'm not sure I'll get back to you super quickly. And I show up at 7 a.m. on the morning of tests. So if you want to swing by before school starts tomorrow, I will be there. Good luck.